From Chicago, welcome to 3Degrees Discussions. I'm your host, Mike Vasquez. This is a podcast devoted to the stories behind the innovators, entrepreneurs, and leaders in the 3D printing industry.
We got contacted by CalREM, actually, who was doing a project with Northrop and some other folks, and wanted to know if we had the capability to service finish TIE 6.4. So we were like, oh, yeah, absolutely. I mean, we've been doing TIE 6.4, air engine compressor blades for 20 years, so no problem. We were maybe a little flippant in that response because these were TIE 6.4 EVM components, right? And we were used to, precision milled components coming with probably a 1624 micro-inch RA. So when these bars came in that looked kind of like, I don't know, honing tools or something, we were a little shocked.
That was Justin Michaud. Justin is the CEO and president of REM Surface Engineering. They specialize in finishing manufactured parts and joins the show today to talk about the history of the company as well as their work in 3D printing. Justin has worked in all segments of the business and has specific domain expertise in the metal AM industry, the wind turbine gearbox OEM and repair industries, and the general gear industry. Justin serves in the American Gear Manufacturers Association Immersion Technology Committee and is a graduate of the University of Notre Dame. Before we get started, head over to www.3degreescompany.com and subscribe to the podcast. Remember, you can listen to the show anywhere you download your podcast, including Spotify, Apple, Amazon, or Stitcher. All right, Justin, thank you so much for joining the show. Excited for the conversation. I think we've got a lot of ground to cover in this episode. So I like to, as you know, get started in the very beginning with kind of where you got your start kind of growing up. And I think in this case, we've got kind of a family story to weave into your own career story. So let's jump in there from the beginning.
Sure. Yeah. So I'm third generation family here at REM Surface Engineering. So yeah, it's always been a part of my life, going back to as a kid, just, evenings, weekends, just being there, being around the company, sweeping floors, mowing lawns, doing that kind of stuff. So it was always something that was part of, kind of my day-to-day life and something that I was always interested in because it was sort of like it's a sciencey type of persuasion. That was always where a lot of my interests lay early on in school and whatnot. So coming out of college, had other options and things like that. But just, the idea of working for the family company and pushing it forward was meaningful to me and something I wanted to keep doing. I like the idea that it's a real technology offering. It's a value add type application. You're not going out there and selling widgets or what have you. Not that there's anything wrong with that, but I like that element of solving problems, helping customers, creating value. So that was how I got started with REM. Worked my way up through just all the different aspects of the company from manufacturing, accounting, service processing, sales, research, all that, and eventually stepped into took over for my father and now running the company. Have been for about 5 years now. So yeah, it's been rewarding. It's nice. Yeah, obviously there's drawbacks because you never leave it. It's 5 o'clock. Doesn't mean that the problems go away very much. You're still thinking about them and they're just waiting for the next morning. Again, obviously everybody has that, but maybe a little more so knowing that it all kind of falls on my shoulders, but it's been a very good experience for me.
And so let's go back to the beginning. How did your grandfather start the company and where are you guys based again? Just put some context around kind of the early days.
Yeah, absolutely. So the company's headquartered out of Southington, Connecticut, and it was founded there in 1965. My grandfather had been working in the research and sales side for especially chemical manufacturer out there. They were supporting the plating industry in New England at the time, and just kind of one thing led to another. He decided he wanted to go out on his own, be independent, so he started the company, and we moved from the first little small rented location to the location where our headquarters are still, I think after a couple of years. Gone through multiple expansions. But the company, it looks a lot different now than it did then, obviously. So that was our single location. And as I referenced, it was supporting alkaline cleaners, specialty cleaners to support the decorative plating application in New England, which over time, a lot of that kind of went away. There's still some of it in that area, but a lot of it went overseas. And that was, fortunately, my father, when he came into the company to work with it and eventually took over from his father, my grandfather, sort of stumbled upon this technology of chemically accelerated vibratory finishing. This premise where you take mass finishing, which is typically just an abrasive scouring type of process, and rather than just having it be effectively like a sanding process, introducing a chemical that's going to react with the surface in a self-limiting way and allow you to refine that surface in any number of ways. Maybe it's more controllable fashion, maybe it's more efficient, maybe it produces less solid waste and allows your vibe processing line to be cleaner and whatnot. So there's a range of reasons you might consider it, but it was, as like a lot of interventions are kind of something you just stumbled upon. And over the course of about 10 years, we pivoted almost entirely away from alkaline cleaners to this being what we do now. And it's been from my time in the company, it's all we've done. Like we don't do anything really with the plating industry anymore. We don't support any of the decorative applications, with the US penny or things like that, which is something that was a big part of our past. It's crazy. I mean, you evolve so much as a company. But it's been a really unique journey. You started with a lot of decorative applications. We still do a lot of that. It's still a very big part of our business. We do all of the pre-nickel chrome plate finishing for like Snap-on and Stanley Black & Decker here in the US still. But over time, that technology was recognized as it might have benefits in other applications. The first sort of I'll call engineered applications were bearings and airfoils back in like the late 1980s. From there, we stepped into gearing. Of course, where do you think that started? Racing, because racing will try anything. And it worked out pretty well. And, now it's still a big part of our business, and we just really evolved from there. Gears is still probably the biggest portion of our overall business. We do a lot in the helicopter, vertical lift takeoff industry for power transmission gearing. Anything where there's a really, you want to increase margins of safety, or you want to have things like, longer loss of lube operation for helicopters and whatnot. There's an advantage to the process. And that maybe, kind of dovetails in a little bit into additive because aerospace is kind of how we got pulled into additive, because obviously aerospace was an early adopter in the metal additive manufacturing area.
And so we'll get to the additive piece in a second, but like paint a picture for me of kind of what does your factory look like, and kind of how do these machines, like when I step into kind of your offices, your factory, your facility, what do people see, and kind of what sorts of parts do people send? Like, what are the typical parts that you saw people send you in terms of size and what condition? Like, what are they looking to get out of it?
Sure. So I should clarify. So obviously, Connecticut is our headquarters. It's our largest facility. We also have our Texas facility, which is primarily our research and development center. We've got a small facility in the Indiana area where we do outsourced processing for local companies, primarily like off-highway, heavy axle, those sorts of applications, just for proximity reasons. And then we got a facility over in the UK, which we've used historically as our access to the European market. We're in the process of acquiring our German distributor to now reestablish a European presence because of Brexit and all that. But so each facility looks a little bit different, but there's some common elements. So with Connecticut being our headquarters, it's where we do the majority of our chemical blending. And it's where we do a lot of our, if you will, kind of like serial production, outsourced processing. So we do business with two ways with customers. So we'll install technology at their shop floor, depending on whatever their needs or applications are and what fits their overall production scheme. And then we'll support them from the initial technical process design side, but then supply ongoing consumables, so the chemicals, the media, and what have you. So, and I can go to the process if it's interesting a little bit later, but so that's one side. Another side is that people will send us parts and we'll execute that for them, right? So really, it's kind of customer dependent. Sometimes folks will do a bridge to installation. They'll process first, get comfortable with technology, let us sort of work out any kinks for their specific parts, and then put it on into their shop. Or sometimes that's just better for them overall. They don't want to make a capital investment, or they don't want to take on the quality requirements, et cetera. So, Connecticut has all of that. So you'd have, your large chemical blending takes, things like that. You'd have a relatively large job shop facility with, range of vibratory bowls ranging from small, less than 1 cubic foot, up to like 20 cubic foot capacity. And you have warehousing and shipping, receiving, and we've got our office, and we've got our accounting situated there, just because it's kind of the largest facility. If you go to Texas now, you're going to have a lot of that, but it's going to be in different sizes. We're not looking to do production runs of chemical blending. We're typically doing stuff just for our in-house uses there. We've got a fairly large outsourced processing capability there. So again, you're going to have a number of vibratory processing bowls, but you also have some of the more kind of experimental type of equipment. You have drag finishers there, centrifugal disc machines, higher energy applications, and that's also where we have installed our some of our newer technology that comes along with the additive side with some of the chemical polishing. Which is pure chemical. So you have some large fume hoods and small fume hoods, because there you're not utilizing this sort of chemical mechanical type of applications, pure chemical dissolution, that we've done some customized work on and has some interesting advantages. So those are kind of you see just similar flavors, but different applications and a bit broader. The UK is very much like just a slightly smaller version of Connecticut. We've got to do a little of everything because they're doing a lot of the blending for the continent there, and it's also doing some of the outsourced processing. And then Indiana would be sort of just like a bit more of like a smaller version of Texas, and that they're not doing any of the R&D. They're set up just as a production shop. So they've got, like 15 different, like relatively large vibratory bowls there, and they just run to specific set processes, and very much more, kind of like serial production type stuff. Whereas Connecticut and Texas, you have some of that, but by and large, you've got a lot more variety. You're seeing a wider range, sort of higher mix, low volume applications coming through there.
So I imagine there's quite a few variables in the process, right? Like there's the chemical piece, whatever the chemical composition is. I assume you kind of match that up to the material. So if material X doesn't like particular solvent, that's probably good for you. And so it helps with the agitation part. But then I'm guessing you have the media and shape and frequency, or kind of how fast you're mixing or kind of density that you're mixing. Are there others that are kind of like from a recipe perspective, whenever you get a new part in, kind of what do you think about in terms of modification to your process to meet the customer's needs?
Yeah, so it's a good question. So, and it varies a bit depending on whether we're talking about sort of like traditional subtractive manufacturing industries, where you get like a ground component, versus on the additive side. Additive, kind of with everything, typically has a bit more complexity to it. So we'll talk about non-additive first, then we can switch over to additive. But yeah, you're 100% right. So in general, like process chemistries, whether we're talking about the chemical polishing or the chemical mechanical polishing, are typically alloy mats. Sometimes it's alloy family. So like some like the lower stainless steels, 17.4, 15.5, 304, those will all work in basically the same process chemistry. As you then step up some of your chemical resistance and whatnot, because we need to react with the surface, right? So chemical corrosion resistance, et cetera, creates a little bit more challenges. So as you step into like a 316, or you get into some of your super alloys, you're getting into different type of compounds. Obviously, carbon steels, very different chemical formulation than titanium. So, that is one of it's a good thing and a bad thing about technology, that we're very specific in that regard, which means that you're getting a fairly tailored solution when you're working with us. But the bad thing is that, like, if you've got a new alloy we haven't worked with before, okay, we might be able to figure out something quickly. We might not, right? It might be a fairly involved undertaking to develop, especially, again, if you're carbon steel, it's probably not going to be too hard, right? But you're getting into like these super alloys, these high hydrogen resistant type, high temperature or refractories. Those become more challenging and typically a bigger effort to develop a capability set there. And again, like you said, talk about media. Media is very much dependent upon part geometry. So we've got a fair degree of expertise in terms of knowing how to match that. So I'll draw a gear as an example, right? The thing you're typically looking at with the gear is what's your root diameter, how tight is your diametral pitch, because you need to be able to have uniform contact on the entire flank, because you don't want to alter that profile, right? That's one of the things that sets us apart from like traditional abrasive mass finishing, is we can maintain geometries to a much higher degree. You're talking like critical aerospace gearing, it's a couple of microns of plus minus from, tip to root there. Otherwise, you're throwing in that tolerance and you're having other sort of issues, which you obviously can't deal with that. You can't just pull over an airplane, the side of the road, so to speak, right? We don't mess around with that. So it's very, very important there. The more you do something, obviously, the better you get at it. We're very fortunate. We've got a lot of really long-term employees. I think our average tenure on the sales and technical side is north of 15 years. So we've got a lot of really great knowledge. We have the job now, as a lot of folks do, we're trying to get a lot of that knowledge, codified into work instructions and databases and what have you. Because you do have with that great long retention, you also have an aging workforce, right? So pulling folks on, that's something that we're actively working on and actively dealing with. But there's some elements to the recipe. Simpler applications, simpler to react materials, things we've worked with a lot. You're really not talking about too difficult of a spin up. You can go from first lot processing to production, easily in about a month's time. For so a lot of these traditional applications. On the additive side, where we've got a lot of incoming variability relative to quality and even printer to printer, or maybe even print to print, you're typically trying to establish some broader boundaries with those process parameters, for that process control, that manufacturability. You're not often able to make that quick of a transition. But I mean, fortunately, Additive's not typically looking for that quick of a transition as they go from prototype to production anyway. So it works out okay.
And so tell us the story about how did Additive come into kind of the company's purview? What was the start there?
Yeah, it's a fun story. So we got contacted by CalREM, actually, who was doing a project with Northrop and some other folks, and wanted to know if we had the capability to service finish Tie 6.4. So we were like, oh yeah, absolutely. I mean, we've been doing Tie 6.4, air engine compressor blades for 20 years, so no problem. We were maybe a little flippant in that response because these were Tie 6.4 EVM components, right? And we were used to, precision milled components coming with probably a 16 to 24 micro-inch RA. So when these bars came in that looked kind of like, I don't know, honing tools or something, we were a little shocked. And some of my R&D guys like, well, what do they want us to do with this, right? And I'm like, well, let's give it our best effort. Let's see what we can do. So, in a traditional, what we call sort of like our ISF process, which is like what we use for precision components, you're talking about a couple of 10 thousandths of material removal, typically, maybe 4, 5, 10 thousandths per surface. That was not going to work with this, 1600 micro-inch RA Tie 6.4 fatigue bar. So it took us quite a while using some of our traditional technologies, but ultimately we were able to get to a decent surface finish. And as luck would have it, it performed really well on the fatigue side. And we kind of got interesting questions back from the folks. It was like, it doesn't look that great. There's surfaces that seem better and brighter and smoother, but yours is performing better. Why is that? To which we said, well, we don't know. But that's information that we're very happy to have. And we'll look a little deeper into this. And so at that point, we sort of kind of backed in and said, okay, what is this whole additive manufacturing thing? Is this something, clearly our traditional technologies are not going to be the right solution because we can't have, weeks of cycle times to get these things done for most applications, which I think it literally was a couple of weeks of processing to get where we needed to go on that one. So digging into it, kind of understanding, the concept of, at the time it was sort of more of like a near net shape application and seeing how much of an issue roughness was, we said, well, this is probably going to be something that's going to be important for us. This was probably about the 2010 time frame. And so I wasn't CEO at that point in time, but I was working a lot with the sales and the R&D team and overseeing operations, and sort of said, hey, let's spend some money on this, right? So we pulled on an R&D guy who spent about 50% of his time just looking into ways to how can we cut these cycle times down? How could we deal with this? And focus really heavily on titanium. And that's really what kind of opened up this chemical polishing, which is really it's just a derivation of chemical milling. We're trying to make it a bit more precise, a bit more focused on you're remediating some of those micronaut features on the surface, flattening the surface as much as possible. You're really getting rid of that granular roughness that you see in those powder bed type components. And that, fortunately, we had some good success there. We really, probably over the first 5 years, that's probably what we did about 90%, which is Tie 6.4. And built a little bit of a reputation there, got in some technical publications and some conferences, and started to be recognized as someone that maybe you could look at for a surface finishing solution. And around that time, that's when Dr. Diaz came on board, who's now our lead AM scientist, and really at this point kind of a recognized expert relative to both surface classification of AM surfaces and this chemical or chemical mechanical polishing. And from there forward, we've really expanded a lot. It's gone from being something that we just did a bunch of fatigue and tensile bars for probably the first 5 to 7 years to now it's a meaningful part of our business, one of the top 10 industries that we work in.
That's awesome. And so as the additive industry kind of matured, or not, I mean, it's not mature by any means yet, but kind of were there kind of, how do people find you? I guess, like, what were was it word of mouth? Like, was it particularly like, hey, like E-beam and tie, like there's not that many people looking around. So like, did you talk to other people? Like what was the start of that kind of part of your business from just a growth standpoint, right? Like as a business, like you're trying to grow this new part of it. Kind of what was your strategy to grow that particular sector?
Yeah, I mean, we were fortunate to trade on some of the reputation that we had, with the traditional aerospace type applications. So, we had some like, the Pratt & Whitneys of the world and folks like that reaching out to us for projects, and they were in they were in their own qualification perspective at that point in time. So it was a good fit. They weren't looking for us to just, give them a plug and play solution. They wanted to do a little bit of research. They wanted to understand how the service finishing process would affect things. And that was really what we did a lot of. Once we started seeing some of these technical benefits, that's really where we always benefited. I mean, if we're not giving it a technical benefit, we may not be the right solution. In some cases, yeah, we can give you some cost advantages. It's typically not as simple as, oh, it's cheaper. It's normally going to be like a total cost of ownership or a total manufacturing process consideration. So it's not like you're not coming to us just kind of as a drop in, right? You come to us because you have a reason, you need a solution or something. When we started seeing some of that, we started going to the traditional route of some trade shows, looking to get involved in some the technical committees and things like that. And we were lucky because the additive industry it's really vibrant in that space. I mean, it's really open. You've got a lot of, presentations of new technology and research that is truly new and novel and actually is something that's more than just, I've got a new machine tool or whatnot. It's not, I love the gear industry, but it's not like that. I mean, and understand, it's been around for 80 years or more. I mean, it's very mature. You're coming on board with a new technology like us. Even though we've been doing it now for 25 years, they still kind of look at the new technology. And a lot of people look at it like, oh, why do I need it? I can grind it. I can adjust some other things, like face width or things like that. And I don't need it, right? So unless you really want to have a new design, folks aren't looking for us there. Whereas in additive, there's a definite need, right? Everyone's trying to figure out how to make parts and how to make, higher criticality parts and what have you. So there's much more openness to that. And that really, it yielded a very nice environment for networking with technical individuals, engineering leads and what have you in both the government and the private sector. You spend enough time with folks, you gain some credibility, you work some projects, and you can get a nice little flywheel effect going. And that's kind of what we're seeing right now. The tricky thing is you don't get forecasts in the additive market like you do in the traditional marketplace, right? So we're always fighting that battle of man, we got a pretty big project backlog here, so we bring some more folks on. We're always kind of juggling that. We're probably always maybe a step or two slow on adding staff in that regard, but it is a nice dynamic in the AM space that you do have this open technical exchange and this real incentive, I think, from people and a desire from people to want to share information, at least to a degree and advance the industry overall.
And you mentioned in kind of some early kind of correspondence that SBIR and was a part of that strategy as well, in terms of you have your core business that has been established around for 20 years, additive's a little bit new, and you've got kind of a foothold, and then there's even other research or other types of areas that you want to explore and kind of augment with the SBIR program. So for those who aren't familiar, I actually just submitted my first SBIR 2 weeks ago. So I think having gone through that process.
Very nice. Congratulations.
It's not.
It's an undertaking.
It's not trivial. So maybe just take a step back and kind of tell people what it is and then how you guys approached it and kind of how it's worked for your business.
Yeah. So for us, I really can't speak highly enough of it. It's been huge for us. So because, we're not like a super small company. We're about 60 people across 4 locations. We've got some solid existing revenue streams. We're profitable. So we don't need SBARs necessarily to survive, right? We're not, waiting for that next seed funding round like a lot of entrepreneurs are and what have you. And that's, that's a route that people can take, right? It's a challenging one for sure. Nothing but respect for folks that are doing that. But I mean, it must be tough because you can have these lags between submission to award and what have you. And it must be a tough dynamic. For us, winning SBARs has been the vehicle by which we've been able to expand our technology offerings. And I mean, really, we wouldn't be doing half of what we're doing today without them. So in that sense, I think we're a great poster child for that. We talked about, TIE was the first thing that we had some success with. We had some pretty good legacy capabilities in TIE from the subtractive market. It wasn't something that was a massive part of our business, but it was a capability that was there. We had very little in regards to addressing super alloys, so Inconel 625, Inconel 718, and what have you. I mean, we've done a little bit here and there, but it was not a core competency. And so just through some of this networking and being a part of the industry, technical exchange and whatnot, we got connected up with Paul Gradle from NASA Marshall. I know you've interviewed, and he's a great guy, really advancing the industry and really doing a lot of good stuff. And so he'd seen some of the presentations, he'd seen some of the data with the titanium. So he was like, hey, this is great. I got some Inconel 625. Can you do it for that? We're like, well, we'll give it a try, but I really don't think it's going to be a great result. And so we did a little bit of small projects with them. And there was enough, he had enough directional belief in it that, we found a SBAR call that was a general fit for our technology. And we were fortunate enough, this is back in 2018. And we won our first SBAR. It was a phase one, just solely focused on Inconel 625, trying to find as we call it, the optimal finishing technique. And we weren't necessarily focused on just our technology. We looked at electropolishing, we looked at like standard chemical milling. We were still kind of early in our chemical polishing days at this point. And then of course our traditional kind of chemical, mechanical type applications. And ultimately, we coming out of that, it really sort of validated what we thought was maybe what we need to do, which was sort of a combinatory approach where applicable, where we'll do like that chemical polishing type application to get maybe 60 to 80% of that roughness reduction you're looking for, get rid of a lot of maybe that granular surface, maybe the contour zone, you got a lot of porosity packed in there. And then if you need more, then you move into that chemical mechanical finishing, where now you can flatten out some of that waviness that's on the surface that you don't see in subtractive parts and what have you. So that was a great experience for us. It was, as I'm sure you know, it was quite an effort to get all the paperwork side and the documentation side, and just understanding how to do those things, because we hadn't done any of those things. Coming out of that one, we said, hey, this was really successful. We want to do more of this. We brought in a guy who had worked at NAVC for a while, running their SBAR programs, and we couldn't do it without him, without question. I mean, navigating those waters, it's a big thing. But fortunately, we've gone on. So like that phase one went to a phase two, which expanded our capabilities then to have 718, a little bit of Haskell-AX, and some novel alloys that NASA's working on, JDK75 and NASA HR1. But there's some side projects on some of their copper alloys, GR-COP2 and GR-COP84, which at that point wasn't a SBAR, just some IRAD and some P-card work and what have you. We knocked out some solutions there relatively easily. At that point, we were really bought into SBARs. We started looking into what AFWorks is doing. I really like their open call submissions that they have, where they're relatively small, $50,000, 3-month sprint, which is it's a lot to get done in that time period. But it allows you to put out premises for a company like us, who it's a little bit more niche. There's not a whole lot of SBAR calls that are like, give me a surface finishing process for this alloy, right? But with $50,000, like the Air Force will take a lot of shots if you can sort of convey a potential mission need. So we did a phase one focused on some Luma 661 RAM 2 material from Elementum, just because we thought it was an interesting novel material, maybe an alternative to the LC10 mag, which is so predominant. That one went on to a phase two with some additional aluminum and titanium alloys. We got a direct to phase two on some Inconel, which is more sort of like almost material offset, like sort of process design strategy focused. We got a phase one recently on GR-COP, looking to optimize that one mainly for like channel applications. It's really, probably, like I said, at least 50 to 60% of our revenue that we're doing in AM is coming from the results of those process developments that we've been able to do, which we wouldn't have otherwise funded. I'm not funding speculative $1 million investment projects. I'm not that big, right? Taking 50 to 100K shots is kind of a big deal for us. We typically only do that if we've got a very defined revenue case at the back end of it. But with SBARs, you don't have to do that, right? You can take these shots. You can build out these data sets that you don't otherwise have the funding to do. I'm not generating a whole lot of fatigue data in my subtractive industries, right? Customers are doing that, and maybe they share it with me in a paper, maybe they don't. But by and large, everyone's duplicating it. I can generate data sets in these SBARs, right? We can do these things that we can then publish ourselves and go to conferences. It's really been a big part of where we our path to getting where we are right now. And the other part of it is, it's putting you in the room with people who are decision makers in these platforms, like Paul, like Dr. Benedict with AFRL, and it opens a lot of doors as long as you can do a good job with what you say you're going to do.
Sure. And so going back to the some of the technical requirements of some of these projects, so you put it through your process. Can you talk a little bit about how do you measure success? Like what's the actual kind of process of measuring surface area? I've seen kind of profilometers and things like that, but like for some of these additive parts, they're complex shapes. So kind of what are you looking at in terms of look and feel, and then quantitatively measuring some of that? Is it just fatigue, or is it other surface finish aspects?
It could be a challenge. So like kind of like looking at it like first from like the traditional industry space. You can normally, like if we're qualifying a process, we're going to have a set cycle time that's going to deliver a set amount of material removal, and it's going to, if we have a known starting roughness, we're going to be able to deliver you a known final roughness, and we'll develop that as a part of like some qualification work and what have you. And because those are super mature processes from the manufacturing side, like what's coming to us, there's generally not a lot of surprises, right? Like that's got a high manufacturability yield. Like you're good there. On AM, different, right? You're not generally going to be able to guarantee a final roughness unless the source of the parts is extremely locked down and extremely controlled, right? Because there is just more variability in the AM process. There's a lot more going on, right? You're not coming you're not taking bar stock or what have you that's then going through a machine. You're forming that bar stock and the shape, and you're doing all that at once, and there's a lot going on there. So we are typically dealing with applications. So there's typically one or two things that we're working with. Either A, we're working to like a sustainment type component or replacement component where there's a print spec that we've got to hit, right? Thankfully, a lot of those print specs are coming from casting type stuff, so your roughness is not all that stringent, right? It's like that, 125 micro inch, 3.2 micron RA finish. That's normally pretty doable as long as we've done the upfront work with the customer to develop what the material offset requirements are going to be. So with enough material, you can normally get to whatever roughness you want. As you get to some of these more complex geometries, maybe it's channels and things like that, that doesn't always, you don't always have that luxury, right? So that's where it gets a little bit trickier. So we can have roughness call-outs as the back end. We don't love RA. We don't love it in the traditional industries. We love it less in additive. SA would fall into that same camp, but it's what everybody kind of knows, understands, and it does give you some directional information. Dr. Diaz would talk to you about needing to look more holistically at like surface texture, and there's not necessarily one parameter that you need to consider there, right? Because an additive, you can have a surface that will have, like, let's say a relatively low R rate, let's say less than kind of 63 micro inch, kind of 2 micron type range, a little bit less than 2 micron range. Kind of a good machine surface, and that surface can perform horribly for fatigue because of the forming process that you did to get that polishing. Maybe it was a purely abrasive process. Maybe you didn't address any of those sort of surface discontinuity micro notches, because at a certain point, the angle of your surface valleys, if you will, becomes impactful for those fatigue applications. On the other side, you can have a surface that looks like a very, very clean, very wavy surface. That's going to have maybe the same RA, maybe even higher RA. That can significantly outperform that comparative abrasively processed surface. And that's something that we've seen in some of the projects that we've done. So it's a difficult space for us. It's a difficult space for like the design and the manufacturing engineers, determining how you specify what you need. So coming away from like the, hitting your sustainment or hitting your legacy print type applications, what is the benefit you're looking for from the surface finish becomes the next question, right? So if it's fatigue, okay, we've talked about some of those things. Realistically, the only thing I can tell you for fatigue right now, if you need a specific surface finish to achieve a specific fatigue life, you need to validate that process and you need to lock in that process. And it's going to have to be managed from a quality perspective by a fixed process, engineering revision control and what have you, because there's not right now enough of a data set out there to be able to correlate this surface with these roughness parameters from this type of process to this surface that's from a different process that might even look very similar. Like electropolishing is a funny one for us. We've been a part of a number of studies. It makes a nice surface. It doesn't have a significant fatigue benefit in the studies that we've been found, even with comparable material removal amounts and comparable roughnesses. And we don't necessarily fully understand that. I don't think anybody does right now, but it's a challenge. If you're looking at for flow, if you're looking at for cleanliness, then there's different things that you can consider there. But so to come back to your original question, so like, what are our quality deliverables? How are we controlling that stuff? I mean, a lot of it is fixed process control. We need to determine what the parameters are that are important for final product quality, and we need to make sure we monitor those in process. We need to have agreed upon material offsets, and we need to have good control on the customer side of them controlling what they're sending to us. Because you really do, unfortunately, see even print-to-print variability. It's not as if every single one is the same. You get we're into issues with folks who are not maybe as experienced in the additive industry that says, oh, well, no, the print guy said he used all the same parameters. Doesn't mean it's the same. I wish it was. It unfortunately doesn't, because I also use all the same parameters, and I can tell you that, okay, your overhanging surface here, they're a lot worse. They were not particularly dense in this going. You must have had something go wrong. Don't know what that might have been, but you got to look into it. So it is a challenging space. And I think that's for that reason. I think a lot of the places where we're seeing a lot of use is in the ultra challenging applications, whereby there's value there to justify it.
Yeah, and I imagine too, like, so when I think of your process, I think of in the context of an additive workflow. It's a post-processing step. But the reality is, if you know that that's your end goal, or that we're going to put it into this treatment, there are certain decisions that likely that would be better informed by a design or materials engineer or mechanical engineer that's designing the part and how it's going in the build and the powder qualities and the parameters. If they know it's going into your process, there are probably do's and don'ts that you want, or things that will make your process more effective, so to speak, right?
Oh, absolutely. Absolutely. I mean, the biggest one is material offset. I mean, a lot of times folks maybe won't think about that they're going to need to do post processing, or they can get away without it. And then you'll come in at the back end and they'll have, I don't know, maybe 25 microns, maybe thousands for you to take off. And they're looking to take it from a relatively higher roughness, in the hundreds of micro inches to something, near single digits. That's generally not going to work. It's just, physics and things like that. It doesn't work that way. Chemistry doesn't work that way. Not for the additive parts. It's just, if you, at a certain point, if you're looking at your RZ, which is typically your average kind of max peak to valley, if that's bigger than what my material offset is, I'm not going to be able to get you the result you're looking for, right? So at a basic level, yeah, thinking about that material offset is super important. We love, I know why people don't like using it, but we love micro X-ray CT scanning. We think it's super valuable because, with these type of processes, you do tend to have, a concentration of porosity, even though these are very, very dense parts. They are, I truly believe, 99.9% plus. If you're going for high finishes, low roughness surfaces, a single pore can throw you out, right? So needing to know where that accumulation might be, how deep is that, right? Is it 100 microns in? Is it 200 microns in? Is it more than that? That is very helpful for us in terms of, well, we don't need to do a whole lot of stop and checks, right? I'm not checking your part after 50 microns of material removal. If I know I've got this nice X-ray CT scan here that shows me you're going down to at least 150, that makes development easier on our side. And it also avoids, you still, because we are a chemical process, right? So you still get people saying, oh, what'd you do to my parts? Well, yes, chemicals can overattack a surface, but they typically can't overattack one surface. If they're all destroyed, yeah, maybe we did something wrong, right? But if just one looks bad, I'm going to tell you it's probably a printing parameter dynamic, and you probably had some subsurface issues there. So that's probably the biggest challenge that we deal with in trying to understand that is, how much material do we need to remove to get the surface that you're looking for, and why are you looking for that surface? Because maybe you've got a legacy call out for a certain roughness, but maybe you don't actually need that. Are you going to be able to test that in a live fashion to determine that what we can produce here within your design offset limitations? Is it going to work for you or not? These are all things we got to juggle when we're kind of getting these new projects off the ground.
So you're really in a unique space in the additive world where you get to see a lot of different industries, a big spectrum of users, from a post sophistication, amount of money invested, the amount of research they want to do or can do. What are your general observations of the industry, kind of as it's become a bigger part of your business over the last 10 plus years?
Ooh, that's a good one. It's a tough one there. I think there's a lot to unpack there. I think you've got, I think you have a broad range of sort of approaches and experience bases in the AM space, which is good. That means it's still growing. You still have people coming in. Maybe it's sort of a little bit in recent years, we've seen some of the consolidation, but it's still a very vibrant, growing industry, which I think that's good. I do think I kind of made reference to it earlier. You do have some folks who come in and think that additive manufacturing, laser powder bed fusion, electron beam, whatever it might be, that's just a machine tool. And it's not just a machine tool. It's more than that, right? I mean, you're doing more things. You're forming the sort of the stock material as you're also forming the shape, and you're doing a lot of things. You're doing different maybe heat treatment processes that you don't maybe do for the traditional places, but it's high static pressing or what have you. So there's some learning curve elements there. I actually don't envy any of the folks who are diving in maybe on the small business side and trying to make this a core part of their business, because I think the knowledge set you need to have to have the expertise and like the capital equipment investment, I mean, it's sizable. You're not just tiptoeing into this. You need to have some big backing to do it well and to do it right. And I mean, I've known folks who honestly had great knowledge sets and just at a certain point, the CapEx is a problem. Unfortunately, a lot of those guys, it's worked out for them. They've kind of been absorbed into larger companies and what have you, and it's worked out really well. But I think that's a big thing is, your funding and the knowledge background has got to be there. And I think you've got some challenging economic aspects as well. I look at a lot of the like the independent print shops, the manufacturing centers and what have you. It's tough, right? They need to deliver to specifications, but they also need to make money, and money is time, and time and the machine and quality often can be a trade-off. So it's a hard space for them to be in. So like I said, I'm happy where I am in. I'm not looking to dive into that world anytime soon. I love working with all of them, and in general, the good thing is that I think almost everybody in the industry is very open, and it's not it's never like really a blaming dynamic, right? If something doesn't go right, if things don't hit expectations, normally we're doing a nice root cause analysis. We're trying to find out where things could have gone better. I do think that there's a lot of development that's still going to come in terms of the machine control, the parameter control, the in-situ monitoring. You're seeing a lot of it. You're seeing a lot of push in those areas, and that's just going to be good for the industry overall. And ultimately, it's going to make it's going to narrow some of the scope of work of what we do down some, which is going to be a good thing though, because it's going to make things more controlled, more repeatable, and it's going to be a broader application set there than maybe what we have right now.
So maybe one final question. So kind of going into 2022 or a couple months in, what industries or what's kind of exciting and that's on your radar from a company perspective this year?
Yeah, so Additiv's really fun in that because it's pulling us into areas that we hadn't been before, fully novel. It's also making some things that we did a while back new again. So like a cool, like kind of like what we used to do and they kind of went away, and now it's coming back would be like kind of like hot side airfoil applications. I mean, that was something that we did a lot of in the 80s, and that went away because you had other technologies that were there. Now with additive, you're designing these really complicated like cooling channel applications in the blades and what have you. Well, there's not a lot of things that can get in there, right? Well, that's one of the things that we've been pretty successful with some of our chemical polishing applications, and that really dovetails into like what I think we're probably the most excited about. What we probably talk about the most is like the space, the rocket engine applications, both with NASA. You've seen some growing interest on the Air Force side, and then commercial space. We did nothing in rocket engines 4 years ago, right? Now it's one of our most important industries. It's cool because the iteration from just concept, to you're talking about simple coupons and sub-size specimens to full-size hardware is really fast, especially within the commercial space. Some of the newer market entrants. And we'll work with some companies who have a bit more slower methodical approach, and we might spend 12 months going through a whole lot of just test specimens and building out material databases and what have you. Others will go from a couple of test specimens to determine some material offset amounts and approximate what surface finish we're going to look like, and the next thing you know, we're flowing our chemical polishing through cooling channels of 15-inch tall rocket engine components, and they're getting hot fired 3 months later. So that's really fun. That's really vibrant. Just to be a part of that industry. Obviously, I think a lot of people think space is pretty cool. Being even play a small role in that, which we do, is really something that's fun. It kind of goes beyond just the business side. It just it's cool to tell your kids, oh yeah, like we're working with NASA on that, or we're working with that company or this company. So that's really rewarding, and we like that a lot. And there's other stuff that is we would never thought we would have been in. I mean, we're doing some work with MIT on unique plasma fusion coupler applications. Didn't know what that was 12 months ago. Now, not that I really know now, but I just know a few words enough to be dangerous about it. Semiconductors, right? The semiconductor industry is really gravitating into AM, and it's super interesting. And I can't say I understand all the reasons they're looking for it. I understand a few of them in terms of part consolidation and complexity that they can do and can get better efficiency in these things. But they're really pushing limits. I think we'll see a lot from them in the next 12 to 18 months in terms of both pushing for new alloys and pushing for adoption of these new complicated designs that are really pushing the limits. I mean, we're seeing channel applications in the 200 micron range, right, which is really challenging. But if they can do it, and if it works off, I understand there's a lot of benefits from a cooling perspective, whether it's on hot cool plates and things like that. So I don't think we're going to be bored or have any issues with cool new applications coming out of the AM space anytime in the near future, which it's good. It's good for everybody. I think it'll keep excitement high, and it'll keep industry growth high.
Cool. Well, Justin, thank you so much for joining the show today, and look forward to seeing you at some of the upcoming shows, maybe AGMA, Rapid, in the coming months.
Absolutely. My pleasure. Thanks, Mike.
All right. Take care.